In this video, we are going to explore the complete evolution of networking in modern software infrastructure. We will trace how data moves from physical hardware servers to virtual machines to cloud environments, and finally into modern container tools like Kubernetes. Understanding these core networking concepts underneath is absolutely essential, whether you are a software engineer, a DevOps engineer, or a cloud architect. If you don't understand the underlying paths data takes, navigating production systems can feel completely overwhelming. To keep this practical and easy to follow, we are going to look at a highly relatable scenario. We'll follow the journey of a food delivery application called FoodDrop, tracking how its infrastructure evolved to route thousands of real-time dinner orders, driver coordinates, and payment records cleanly across the internet as the company grew over the years. Let's dive in. When FoodDrop first launched, the entire platform ran on a single physical server. This was just one powerful computer machine sitting in a local data center, running our customer ordering app, our restaurant matching logic, and our driver database all on one motherboard. Because customer phones across the city needed to upload order data to our application, our server needed to be identified on the internet somehow. This is exactly where IP addresses come in. Think of an IP address like a physical street address. Just as a physical restaurant has a unique address so a delivery driver can pick up a meal, our server needs a unique digital address so clients can find it. It looks like a string of numbers separated by dots, for example 203.0.113.10. When data packets arrive at this address, they enter the server through a network interface, which is the physical gateway or network card on the computer, typically labeled ETH0. Think of ETH0 as the main entrance door of the restaurant building. All incoming data traffic must use this door. Once inside the server house, data needs to reach the correct internal program. This is the role of ports. Think of ports as individual service counters inside the restaurant. Our customer ordering application lives at the counter labeled port 80 or 443. Our driver coordinates database lives at the counter labeled port 5432. The computer's operating system acts as the shift manager, reading the port number on the incoming packet and delivering it straight to the correct counter. Of course, hungry customers don't want to type numbers like 203.0.113.10 into a browser or app config. They want to connect to fooddrop.com. To handle this, we use the Domain Name System, or DNS. DNS is the internet's phone book. It automatically translates human-readable names directly into the numeric IP address of our server, allowing orders to fly across the network seamlessly. Running everything on a single physical machine worked at first, but it had major drawbacks. If a heavy database report crashed the server, the customer ordering system froze entirely. If a massive surge of orders happened during the Friday dinner rush, the whole system ground to a halt. To solve this, FoodDrop moved to virtualization using virtual machines, or VMs. Virtualization is like converting a large single restaurant building into a shared commercial kitchen complex. Instead of giving one tenant the entire space, we split the physical server into multiple isolated, self-sufficient stalls. Each stall, or virtual machine, gets its own dedicated slice of the computer's CPU, memory, and storage, and runs its own separate operating system. All of this is managed by a software supervisor called a hypervisor, which handles the sharing of physical hardware while keeping the environments completely separated. Now, how does networking work inside this complex? Each VM stall gets its own unique internal room number or private IP address, such as 10.0.0.5 or 10.0.0.6. These internal addresses are completely hidden from the outside internet. The VMs can talk directly to one another down the private hallway of the building without their messages ever leaving the physical machine. Each virtual interface is guarded by an internal firewall that acts like a security guard, checking incoming packets to make sure they are safe before letting them through. When a VM needs to talk to the wider public internet, the hypervisor uses network address translation, or NAT, to safely pass messages out through the building's main public address. As FoodDrop expanded across multiple cities, managing physical hardware buildings became too costly. We needed dedicated teams just to fix physical machine components and manage wires, so we moved to the cloud. Moving to a cloud provider like AWS or Google Cloud is like renting a completely private custom wing inside a massive, professionally managed skyscraper. In cloud networking, this private wing is called a VPC, or Virtual Private Cloud. Your VPC is entirely isolated from every other company renting space in the same data center. Inside our private VPC wing, we set up separate secure zones for different tasks, which are called subnets. We create a public subnet, which is like our customer reception lobby, with doors and windows facing the public street. This zone holds our user ordering interfaces, allowing public internet traffic to freely come in and browse restaurants. Deep behind this lobby, we create a private subnet, which is our secure interior vault. This zone houses our historical driver payment records and credit card processing logic. They have no direct windows to the street, meaning uninvited visitors from the internet can never see them or touch them. To guide data safely through these zones, we use route tables, which act as the building's navigation directory, showing packets exactly where to travel. We also station security groups, our digital security guards, at every single door to enforce fine-grained firewall rules, ensuring only authorized data packets can move between rooms. Eventually, running full virtual machines with massive operating systems for every minor service became too heavy. FoodDrop decided to break its application into tiny, independent pieces called microservices, separating order tracking, menu layouts, and processing reviews. This is where containers come in. A container is like a portable, fully stocked toolbox. Instead of building an entire kitchen stall with its own utilities and layout, you just pack the code, the tools, and the exact configurations an application needs inside a single box. Containers are incredibly lightweight because they share the host computer's underlying core system, meaning they launch in milliseconds. When you run multiple container toolboxes inside a cloud server, Docker builds a private internal hallway for them called a virtual bridge. Each container gets its own internal desk phone extension or IP address. They can talk directly to each other through the bridge using their container names, like dialing menu layout or review processor, to allow real user phones walking on the outside street to access a specific containerized application. We use port mapping. We tell the host machine when a public call comes into your main line on port 80, automatically forward that request down the internal bridge line to the order tracking container living on extension port 8080. This cleanly links outside customer traffic directly to the exact microservice it needs. When FoodDrop grew to hundreds of container toolboxes running across dozens of different cloud servers to handle nationwide delivery demands, tracking them manually became completely impossible. That is when we reached the modern era of networking and turned to an orchestration tool, Kubernetes. Kubernetes acts as our master city planner. It links all our separate servers into one massive, flat network using a standard called a CNI, or Container Network Interface. The CNI automatically sets up a virtual network cable for every single pod, the wrapper holding our containers. It ensures that every pod gets its own fully routable IP address, allowing any container to talk to any other container across the entire company network with zero port mapping tricks required. Because these containers are temporary and their individual IP addresses change whenever they restart or update, Kubernetes gives us a permanent feature called a service. A service acts as a static, never-changing department hotline number. No matter how many individual container employees change desks in the background, the hotline phone number stays exactly the same, safely load balancing order data to healthy pods. Finally, to manage how public visitors enter this massive network, we use a Kubernetes ingress. Ingress is like the grand reception entrance of our entire cluster. Instead of forcing visitors to navigate hundreds of separate gates, they knock on one single front door. The ingress receptionist reads the path written on their request, directing /orders to the processing department and /menus to the catalog department, keeping the entire ecosystem incredibly secure and organized. From the early days of plugging a single computer into the wall, all the way to building global systems like Kubernetes, the core rules of networking have stayed exactly the same. Everything requires an address to be identified, strict rules to control what traffic is permitted, human-readable names to locate resources, and clear routes to guide data packages to their final destination. Once you understand these 4 basic blocks, you will feel completely confident designing or troubleshooting any modern cloud application. Which phase of FoodDrop's networking journey made the most sense to you? Let me know in the comments below. Thank you for watching, smash that like button, and subscribe to keep building your cloud foundations.